The Global Maritime Distress and Safety System, GMDSS, was developed by the International Maritime Organization, the IMO. GMDSS is an internationally recognized distress and radio communication safety system. The system uses satellites and digital selective calling technology to provide an automatic means of receiving and transmitting distress alerts. The GMDSS system is primarily a vessel-to-shore alerting system. The Rescue Coordination Centers, RCCs, receive distress alerts from ships and then coordinate the rescue. The system also provides a vessel-to-vessel distress alerting feature. Other types of messages that could be transmitted by the system are urgency, safety and routine communications, and safety information broadcasts, for example, navigation warnings, weather forecasts, and rescue messages. GMDSS uses 4 coverage areas: A1, A2, A3, and A4. These areas together cover the sea areas of the world. Sea Area A1 is an area within very high-frequency VHF range of a coast station fitted with digital selective calling, DSC. This range is about 30 to 40 miles. Sea Area A2 is an area with medium-frequency MF range of a coast station fitted with DSC. This range is about 150 miles. Sea Area A3 is an area covered by the Inmarsat satellite system, excluding Sea Areas A1 and A2. Sea Area A4 is basically the polar regions that are not covered by the other sea areas. Depending on how far from shore you will operate your craft, the following minimum GMDSS equipment should be on board. Remember, you're not limited to having only the minimum recommended devices. In an area of operation up to 5 miles from shore, it's recommended that you have a handheld waterproof VHF radio on board. In an area of operation up to 30 miles from shore, a handheld waterproof VHF radio and a VHF DSC fixed radio installation. Up to 60 miles from shore, a handheld waterproof VHF radio, a VHF DSC fixed radio installation, and a Navtex receiver. Up to 150 miles from shore, a handheld waterproof VHF radio, a VHF DSC fixed radio installation, a Navtex receiver, an EPIRB, an MF DSC radio installation, and a SART. Over 150 miles from shore, it's recommended that you have a handheld waterproof VHF radio, a VHF DSC fixed radio installation, a Navtex receiver, an EPIRB, an MF DSC radio installation, a SART, and Inmarsat satellite communication. Radar gets its name from a system of radio detection and ranging. How does radar work? Radar transmits short pulses of radio waves that travel outwards, basically in straight lines. When these waves hit a surface, like a vessel or a buoy, some of the waves are returned. By measuring the time difference between transmission and reception of a reflected wave, the distance to an object can be calculated. The direction in which the scanner is pointing when it receives the reflected wave represents the bearing of the object. Radar systems comprise 3 basic components: a transmitter and a receiver unit, also called a transceiver, an antenna, also known as a scanner, and a display unit. In many radar units, the transceiver is located in the scanner. Radar signals travel along the line of sight. Therefore, the detection of targets depends on the height of the radar scanner and the height of the target. Marine radars operate either on the X-band frequency, 9,000 MHz, or on the S-band frequency, 3,000 MHz. A shorter wavelength allows the use of smaller antennas, therefore on most small boats, the radar used are in the X-band frequency. However, S-band radar has an advantage. It can penetrate precipitation to a better degree, and therefore can detect targets which may be obscured in heavy rainfall. This is a radar display unit. The display unit has controls for the following purposes: the function control, range selector, the brilliance control, the tuning control, the tuning indicator, the gain control, the anti-C clutter control, and the bearing cursor ring. Review the controls. Use the mouse to roll over them. The function control has 5 positions, which are: radar off position. At this position, the radar is not in operation, and there's no power supplied to the display or to the scanner. Standby position. In this position, the radar can be brought into use whenever it's required. The scanner is rotating, but no radio waves are being transmitted. Radar on position. In this position, it takes 2 to 4 minutes for the radar to be in full operation. Radio waves are being transmitted and the received echoes from targets are amplified and displayed on the screen. Range rings bearing cursor. In this position, the range rings on the screen are illuminated together with a bearing cursor and the bearing scale window. Heading alignment position. In this position, the picture of the screen synchronizes with the aerial and brings the heading marker into position. Range selector position. The range selector is used to select the range that the radar will cover. There are 5 positions indicated in miles: 1.5, 3, 6, 12, and 24 miles. When the range is selected, the distance between the rings is determined automatically. Brilliance control. By using this control, the background illumination of the screen can be adjusted. This allows better visibility of amplified echoes and noises appearing on the screen. Tuning control. This control allows the receiver to be tuned to the same frequency as the transmitter. Tuning indicator. This is a visual electronic aid that helps to tune the radar quickly and accurately. Adjustment of the knob to display the narrowest gap corresponds to optimum tuning. Gain control. This control allows the user to vary the strength of echoes appearing on the screen. Anti-C clutter control. The main use of this control is to reduce the strength of C clutter or echoes from waves near the ship, so strong targets, for example small craft, buoys, etc., can be clearly distinguished. This control reduces the gain level only over a short range. The knurled ring is used to rotate the bearing cursor over the face of the screen, which allows the user to measure the bearings of the targets. The echo sounder is an important and necessary electronic navigation instrument that determines the depth of water under the keel. This instrument is one of the prime considerations for safe navigation. An echo sounder consists of the transducer and the display. The transducer transmits ultrasonic waves through the water. The wave strikes the seabed, and part of the wave is then reflected back and received by the transducer. Knowing that the ultrasonic wave travels through water at a nearly constant speed of 1,500 meters, 4,921 feet per second, at a temperature of 13 degrees Celsius, at a salinity of 35 parts per thousand, the depth can be determined by calculating the time difference between the transmission and the reception of the ultrasonic wave. The determined depth information is converted into visual or graphic form. Satisfactory echo sounder performance depends primarily on the transducer installation. The most common transducer installation is a transom mount. The transducer should be mounted at the bottom of the hull as close to the keel as possible and 1/3 aft so that turbulent water from the bow and propeller noise do not affect its performance. The transducer should preferably be mounted on the side of the boat where the propeller chops down into the water to avoid aeration and turbulence. Performance can also be negatively affected if the transducer is mounted near engines, alternators, or seawater inlets and outlets. The most common and basic echo sounder controls are the illumination control, which regulates the illumination of the panel and other controls, the range selector that selects the basic ranges according to the technical specifications. In position 0, the echo sounder usually switches off. The gain control, which regulates the amplification of the received signals. Using the gain control, we can eliminate the multiple echoes that appear when navigating in shallow waters. There are 3 main types of echo sounders: the neon rotating display echo sounder, the echo sounder that produces a continuous record of the depth of the water using electrolyte paper, and the digital echo sounder. Other echo sounders have multicolor displays and show not only the depth of the water, but different types of seabeds, sunken wrecks, and even schools of fish. The simplest form of an echo sounder is a lead line, 60 feet long, attached to a 1 to 1.5 kilogram lead weight. In the base of the weight is a cavity used for taking seabed samples, which are useful when piloting or anchoring. The line has a series of marks along its length. When dropped into the seabed, the marks are used to measure the depth of water. The lead line can be used as a backup when there are concerns about the reliability of the echo sounder. The Global Positioning System, GPS, is a satellite-based aid to navigation system placed into orbit by the United States Department of Defense. The system consists of 24 satellites orbiting the Earth twice a day at an altitude of about 12,000 miles. GPS satellites are powered by solar energy. Backup batteries are installed on board to keep them running in case of a solar eclipse. The system provides highly accurate worldwide positioning and navigation information 24 hours a day. A GPS satellite signal contains 3 different kinds of information: a pseudo-random code, ephemeris data, and almanac data. The pseudo-random code is the identification code of the satellite, which on a GPS receiver is displayed as a number. Ephemeris data contains information about the status of the satellite, healthy or unhealthy, current date and time. The almanac data informs the GPS receiver where each satellite is positioned at any time. The satellite transmitting the data contains orbital information for that satellite and for every other satellite in the system. How is a position determined by satellites? A GPS receiver knows the position of the satellites by the data each satellite transmits. The receiver estimates how far away a satellite is and knows that it's positioned somewhere on the surface of an imaginary sphere centered on the satellite. For each satellite, the receiver determines the size of the sphere. The receiver is located where the spheres of the satellites intersect. To obtain a two-dimensional fix such as latitude and longitude, 3 satellites are necessary. To obtain a three-dimensional fix such as latitude, longitude and altitude, 4 satellites are necessary. The positional accuracy of the GPS system lies between 5 and 15 feet. Differential GPS receivers obtain an even higher accuracy. Differential GPS, DGPS, works by placing a GPS receiver that is a reference station at a known location. The station measures the ranges to each satellite. Then it uses the measured ranges and the actual ranges calculated from its known position. Measured ranges can contain errors such as ephemeris data errors or internal receiver noise. The difference between measured and calculated ranges becomes a differential correction. The differential correction is then transmitted to the DGPS receivers. This is a GPS receiver. GPS stands for Global Positioning System. There are various components and controls used on the GPS receiver. The antenna, which receives the radio signals from the GPS satellites, the power button, which turns the power on and off, the light button, which lights the display for 20 seconds, the display, the cursor control buttons, which move the cursor to input or select, and the character search buttons, which allow the user to select the characters to input or to select a function. On the GPS receiver, we can also see the track button, used to enter the track mode, the edit button, used to enter the edit mode, the navigation button, used to access the position mode, the set button, which allows control over the power-saving function, the clock display, and the distance display, the pause position button, used to enter the position mode, the clear button, which allows deletion of any unnecessary data and allows initialization of the receiver, the enter button, which is used to enter data or execute a command, the recall button, which returns the user to the previous display, the mark button, which stores the present position, and the extension display select button. By pressing this button in nav and track mode, the graphic or character display can be selected, and in pause mode, the date and time will be displayed. The GMDSS system uses the following communication devices: DSC radios, EPIRBs, SARTs, Navtex, and Inmarsat. Let's have a closer look at each piece of equipment. DSC radios provide an automatic means of transmitting and receiving messages. VHF DSC radios keep an automatic watch on channel 70. On channel 70, which is a non-voice channel, an alarm will sound when there's an incoming call for your vessel or an all-ships call concerning urgency or safety, a distress call, or a distress relay. Subsequently, the radio will indicate the channel for additional communication, such as channel 16 for distress work or channel 72 for ship-to-ship communication. Navtex is a worldwide automatic reception and broadcast system. Localized medium-frequency stations supply maritime shipping with vital information such as navigational and meteorological warnings and urgent information. This information is printed out or displayed automatically by Navtex receivers. All Navtex broadcasts are made on 518 kHz from localized stations situated worldwide. Navtex users can set their receiver to specific message types, such as ice reports or sat-nav messages, and can reject others. However, navigational warnings and search and rescue information, including pirate attack warnings, cannot be rejected. EPIRB stands for Emergency Position Indicating Radio Beacon. The most common EPIRB operates on 406 MHz using polar orbiting satellites. It's the simplest means of communication, providing only one-way communication. The EPIRB transmits a distress signal via a satellite system, which calculates the distress position and relays the information to the nearest rescue coordination center. Most 406 MHz EPIRBs also transmit a signal on the 121.5 MHz frequency, which allows search and rescue units to obtain a radio bearing of the EPIRB. The 406 MHz EPIRB is attached to the vessel with a hydrostatic release, which lets it float free in case the vessel sinks. It's very important to register your EPIRB with the appropriate national authority so that when you activate your EPIRB, your vessel details, in other words name, size and type of vessel, are known immediately to the RCCs. SART stands for Search and Rescue Transponder. The SART is solely a homing device for the search and rescue units and operates in the 9 GHz frequency band. The transmitted signals from the SART are displayed on an X-band radar screen, providing a visual indication of the distress position. The Inmarsat organization operates a constellation of 4 geostationary satellites. Geostationary means that the satellites rotate at the same speed and direction as the Earth. The satellites are able to transmit voice, fax, telex, and data communication. Satellite communication should be considered when cruising outside the MF range of a coast station. Considering the cost of a satellite installation, the Inmarsat C may be the most appropriate installation for small craft. Note, Inmarsat C is only capable of sending text messages.